Welcome all. Welcome to the lecture 2 of the series of lectures in the topic Engineering Mathematics. We are discussing Unit 1. I am UV Manoj Kumar, Assistant Professor of Mathematics, Vignan's Foundation for Science, Technology and Research, Vadlamudi. In my previous class, I have discussed about various types of matrices and I also defined what is rank of a matrix. Now we will recall the definition of rank of a matrix. Before going to the definition of rank, we will discuss minor of an element and minor of order k. If in a matrix we consider a square submatrix of size k by k, then its determinant is said to be minor of order k. See here, in the example 1, 2, 1, 4, 2, 6, 2, 3, 7, I am considering a 2 by 2 minor. I am considering a square submatrix of size 2 by 2 and its determinant is minus 1. So, this minus 1 is minor of order 2. This number minus 1 is minor of order 2. Minus 1 is minor of order 2. If the final answer becomes 0, then we say that it is a vanishing minor. If the final answer is non-zero, if the final answer is non-zero, then we say that it is a non-zero minor of order 2. So here we have a non-zero minor of order 2. Come to the definition of rank of a matrix. Consider any matrix, either a square matrix or a rectangular matrix. Then what we want to do? We want to find the rank of a matrix. We can say the rank of the matrix is small r if there exists one non-zero minor of order small r and every minor of order r plus 1 or more should vanish. Okay. What are the methods to find rank of a matrix? There are 3 methods what we are discussing in this content. They are finding the rank by definition, finding rank by echelon form, finding rank by normal form. First we will see how to find rank of a matrix using definition. See the problem on the board. Find the rank of A where A equals to 1, 3, 4, 2, 2, minus 1, 3, 2, 3, minus 5, 2, 2. Is it a square matrix or a rectangular matrix? There are 3 rows and 4 columns. So, size of the matrix is 3 by 4. Size of the matrix is 3 by 4. Therefore, it is a rectangular matrix. So, we want to find rank of the matrix by definition. So, the matrix given to us is capital A equals to 1, 3, 4, 2, 2, minus 1, 3, 2, 3, minus 5, 2, 2. I want to find rank of this matrix by definition. So, what is there in the definition? There exists a minor of order r which is non-zero. Then rank is said to be r. So, definition based on minors. Minors are nothing but determinants of square submatrices. So, in this matrix What is the possible square submatrix of highest order? So this is a 3 by 4 matrix. This is a 3 by 4 matrix. In this matrix, the maximum possible minor will be of order 3 by 3. How many are there? See here, if I consider first 3 columns, if I consider first 3 columns, I will get this square submatrix and I want to find its determinant. How to find the determinant of a 3 by 3 matrix? Select any one row. I am selecting first row. What are the elements of the first row? 1, 3, 4. So multiply 1 with its minor. How you will get minor of 1? Remove the row of 1 and column of the 1. So 1 is here. If I remove this row and if I remove this column, what remains is this part. So 1 into -1, 3, -5, 2. Then you have to change the sign. -3 into minor of 3. Minor of 3 is obtained by removing the row and column containing 3. So if I remove row and column containing 3, then I will get determinant 2, 3, 3, 2. Again, change the sign. So minus becomes plus. 4 into 4 into minor of 4. How to get minor of 4? Remove the row and column containing 4. So what remains? The remains is 2 minus 1, 3 minus 5. So simplify this. 1 into determinant of a 2 by 2 matrix, AD minus BC, minus 2 AD minus BC, minus 15. Minus of minus becomes plus 15. So that is the simplification of first term. Next, minus 3 into determinant of this 2 by 2 matrix. 2 into 2, 4, minus 3 into 3, 9. Coming to the third term, plus 4 into this determinant 2 into minus 5 minus 10 minus minus 3. Minus of minus becomes plus 3. Simplify this. 15 minus 2, 13 into 1, 13, 4 minus 9, minus 5 into minus 3, minus into minus becomes plus, 5 into 3, 15, plus minus 10 plus 3, minus 7 into 4, minus 28. So what is the answer? 0. Now there is a matrix capital A. For that there is a 3 by 3 minor whose determinant is 0. What we want? We want a non-zero minor, but this minor is becoming 0. So what we have to do? We have to search for another minor. So the minor we selected given 0 result. That means it became vanishing. So we will select another minor of order 3 by 3. This time I want to select a minor of columns 2, 3, 4. Another minor of order 3 by 3 is considered here. So we will find its determinant. Three into 6 minus 4 minus 4 into minus 4 into its determinant, its minor, minus 2 minus of minus 10 plus 10 plus 2 into minor of 2 minus 2 plus 15. So if we simplify this, this is 2, 2 into 3, 6. This is 8, 8 into 4. This is 15 minus 2, 13, 13 into 2. So the end result is 0 again. Similarly, if you check, you will get determinant of the remaining two submatrix of size 3 by 3 becomes 0, which means all minors of order 3 are becoming 0. Therefore, rank of the matrix need not be 3. Therefore, rank of the matrix is not equals to 3. So what we have to do then? We have to go for next possible minors. After 3 by 3, next possible size of minor is 2 by 2. See, the given matrix is of size 3 by 4. We are starting with the maximum possible order of the minor maximum possible order for the minor is 3 by 3 and all of them are becoming 0. So we are going for searching minors of order 2 by 2. We take this part as my second ordered minor. What happens to its value? 4, 2, 3, 2. Determinant of this minor, 2 by 2 minor selected equals to 8 minus 6, which is equals to 2. So, there exists a minor of order 2 which is non-zero and all minors of order 3 are becoming 0. So, it is satisfying the definition. There exists a minor of order r which is non-zero and all minors of order r plus 1 or more becomes 0. So here r is 2. There exists a minor of order 2 which is non-zero and all other minors of order 2 plus 1 means 3 or more are becoming 0. Therefore, by definition, rank of this matrix is 3. Therefore, rank of A equals to 2. Therefore, by definition, rank of the given matrix is 2. Okay. Similarly, there is another problem here where rank is given as 2 and you have to find the value of B. I am giving you this problem as exercise. You complete this problem and find the value of B suitably. When we are discussing about finding rank, we said that there are 3 methods. First method is by rank, second method is by row echelon form, and third method is by normal form. Here we are discussing what is row echelon form. Row echelon form of a matrix. A matrix is said to be in a echelon form or row echelon form if the number of zeros before first non-zero element in a row increases with the row number. I am repeating the definition again. A matrix is said to be in echelon form or row echelon form if the number of zeros before the first non-zero element in a row increases with increasing row number. See here, there are 2 examples. In the first example, if you count zeros, 1 0 here, 2 zeros here, 2 zeros here. No, you should not count all zeros. You should count only those zeros which are before a non-zero number. This is a non-zero number. This is a non-zero number. So you should count this 0. So how many zeros are there? 1. This is a non-zero number. Before this, how many zeros are there? 1. This is a non-zero number. Before this, how many zeros are there? 2. Number of zeros before first non-zero number should increase with row number. Are they increasing? Here 1, here also 1. They are not increasing. So this is not in echelon form. First example is not in echelon form. Come to the Second and third examples. Second example, see the first row. Are there any zeros here? No. So the number of zeros here are 0. Number of zeros are 0. In the second row, there are 2 zeros. You should not count both. Only count 0 before 2. This is the non-zero number. Before this non-zero number, how many zeros are there? 1 zero is there. So 1. In third row, non-zero number is this. Before that non-zero number, how many zeros are there? 2. So, zeros before first non-zero number are increasing here. 0, 1, 2. Number of zeros are increasing. So, this is in echelon form. Similarly, see here, these are the non-zero numbers. First non-zero number in row 1. First non-zero number in row 2. How many zeros are before them? 1 zero here, 2 zeros here, and how many zeros are here? 3. So, here also number of zeros before first non-zero number increasing. 1, 2, 3 is the count. So, it is in echelon form. This is not in echelon form because number of zeros are not increasing. 1, 1, 2, 1 and 1 both are same. It should be increasing. Number of zeros before first non-zero number should be increasing. Another form, normal form. A matrix is said to be in normal form if it can be reduced to this form. What is this form? This is identity matrix of size R by R. Identity matrix is a square matrix, and remaining all elements should become zeros. So, this is an example. If you consider this part, that is identity matrix of size 2 by 2. So, this is I2. This part is I2 and remaining all are zeros. So, this is in normal form. This is in normal form. If you are able to reduce a given matrix into this form, IR 0, 0, 0. So, there should be an identity matrix and remaining all elements should be zeros. If you are able to reduce the given matrix like this, then this is said to be normal form of the given matrix. Now we will discuss about elementary row operations or elementary row transformations. Elementary row operations or elementary row transformations are used to reduce a given matrix into either echelon form or normal form. So what are the different row operations we can apply? There are 3 different types of row operations that we can apply. First one is interchanging of 2 rows. Second one is multiplying a row with a non-zero constant. Third one is multiplying a row with a non-zero constant and adding the result to another row. So whatever the results, whatever the operations we are applying on rows, the same can be applied on columns also. So here interchanging of 2 rows Ri and Rj is denoted by Ri if and only if Rj, or Ri implied and implies by Rj. Multiplying a row Ri with a non-zero constant C. So Ri goes to C into Ri. C should be non-zero. Multiplying a row Ri with a non-zero constant and adding the result to another row called Rj. So see, this is the operation. So in these 3, here we are interchanging Ri and Rj. Here we are changing Ri into C into Ri. So existing Ri means row I is replaced with CRi. Here also Ri is replaced with CRi plus Rj. So we are changing a row by a suitable row operation. These row operations allows us to reduce a given matrix into echelon form or into a normal form. So here are problems in which you are asked to find rank of a matrix by reducing it into echelon form and into normal form. We will discuss these problems and we will discuss how to apply row operations and find the ranks of the problems given here in the next lecture. Thank you all.